new innovations. And software has figured this out over the last couple decades or so. We've been evolving software so they can more quickly deliver value. For those of us that build cyber physical systems, the hardware is lagging to some degree. So we really need to motivate those hardware engineers that love sitting in their cubes doing their one little piece of the design to saying, hey, we need you to get on board here with this Agile transformation. That's really what the goal of this talk, as well as the new course, is focused on. So when we talk about this, we show this digital disruption. And if you go to the Skilled Agile Framework website and click on the business agility, this is how we're framing the demand for business agility, right? It shows Carlotta Perez here, and she's done some analysis. Granted, this is about 15 years old or so. She did this back in the early 90s. She looked at previous revolutions where there was an installation period where there's a lot of capital floating into, industrial revolution or steam and railway or oil and mass production. A lot of capital floated into, for example, in the automotive industry. At Detroit in the early 1900s, there were 300 or more automotive companies. And, fast forward 20 or 30 years later, there were 3, right? So as that turning point occurs, right, the winners, the people that are going to win in that space start to reveal themselves, and they start being able to take that capital and produce the new products and accelerate past the other organizations. But that also gives them the ability to move into other markets. For example, who thought that Amazon would be a grocery store, or that Google would be a car company? When Google came out 20 years ago, there was a great search engine, and look at what they are today. They've got business applications, they've got vehicle companies, they're looking at space things as well. So that capital allows them to do a lot of things and move into emerging markets. Well, this isn't just for software companies, right? If you look at the companies on the right, all those are hardware companies, right? Apple is the #1 watchmaker in the world, believe it or not. I remember back in my younger days, everybody wanted a Timex, but that's not the case anymore, right? It's all those people, Apple, Amazon, they build and design their own routers, chipsets, network interface cards. So there's a lot of hardware development going on, even to many of those companies we think of it as being software centric. So this digital revolution is not just software, right? That's a key message. Where are we? So I look back here. I apologize, I moved ahead here real quick. If we look back on Carlotta Perez, she says, there's going to be a turning point, which is somewhere in this decade or so. And many are arguing we have turned, right? That if you haven't made the transformation to the digital age, you may not survive, right? And it's probably true. If we look at the automotive companies that exist today, and we look at the move in the automotive industry towards more vehicle platforms and transportation as a service instead of buying a car, will all the automotive brands that we see today going to be here a decade from now? If that is the trend, and the Lyfts and the Ubers and the Neuros, they start disrupting that space. So a lot of people would say we have passed that already. For example, the market cap of Tesla, these are old numbers, by the way. Tesla's actually doubled that in their market cap over the last year. It's crazy. But they are the second largest automotive company in market cap behind Toyota. Yet they produce quite a few less cars and generate less revenue than those other companies. As I mentioned, Apple's the biggest watchmaker today. So we have really kind of crossed that chasm in the move to the digital age, is the message. There are several aspects relevant to safer hardware development. When we think about hardware, we commonly think about handing fixed requirements to engineers and having them build their solutions. Yet we're not that smart up front. So we need engineers to be thinking, hey, we're going to allow requirements to evolve, and the systems and even the hardware designs that you come up with, they're going to evolve too. We're going to be incremental in how we build these things. We need to focus on the customer, right? We're very customer centric. So the solutions that we produce, and we got to communicate that to our engineers. Who are the customers of hardware? Certainly the end users one, but are there other ones? Manufacturing, data, people that use the data that hardware folks generate, assembly people, the operators that have to replace and maintain these systems. Those are all customers of hardware. We have to be focused, customer centric, and empathize with those people, do journey maps, and understand them well. So we also want to design solutions that can change, right? So that was the outline we talked about before. We want to design for change. And a key one is organizing around value. Historically, these types of systems were very functional focused. We strive for great functional excellence, which certainly is important. But as we see with silos, functional excellence in the place of flowing value across the value stream is cause a lot of delays, a lot of handoffs, and we get a lot of benefits from organizing those people around a lean flow. We want to replace our fixed schedules with backlogs and roadmaps. So instead of assuming that we've got a perfect schedule and never getting any feedback on it, so long as everybody meets the schedule, the program's going to be, your project's going to be successful. We want to replace that mindset with one of learning and innovating, aligning on a common cadence with aligned backlogs and roadmaps that are consistently adjusted. We also want to build and demonstrate. We want to incrementally build and demonstrate that system frequently, as quickly as possible. That's not saying that we're going to ask every hardware engineer to manufacture a new part every iteration, but it certainly means that they can provide we can learn something and provide new knowledge and new guidance, right? What can we learn each iteration? And last but not least, we have to build quality into these systems, right? Not just the software sides, but we have to build the quality of the hardware sides. It's a great message that Agile really originated in product development. If you look at Scrum's roots are in the rugby phrase of the article New Product Development Game, which is all the way back in 1986. And really Agile kind of adopted those practices and brought them into Scrum, and the notion of aligning teams and having uncertainty, right? Management doesn't tell them what to build; they give them a vision and a direction, and it's uncomfortable with the teams, but that's a good uncomfort because they got to figure it out. Agile has adopted those practices in software space, and it's really just surprising that hardware didn't adopt those, because all the examples in there are computers and printers and really hardware type systems. So the message is that Agile's roots are in product development, not software. So don't think that it's a software thing. But the software community does have a head start. As we mentioned, they kind of got here first. They took those ideas and ran with them. So while if we look at kind of the adoption curve, right? If you're doing Agile as a software organization, if you're not doing Agile, you're kind of in the laggard, right? A mass majority of the world has adopted Agile for software. That said, for hardware, these people are really the early adopters, the people that are trying to be more continuous about delivery. SpaceX, Musk is challenging his SpaceX group, saying we need to build a new rocket every week, right? Shockingly, instead of building one rocket, designing the perfect rocket and building it, so we have to learn faster, right? We have to have a pipeline of rockets because we know we're going to expend them, and we need to integrate them more frequently to be able to learn. So that kind of mindset and challenging and 3D printing more than we are, fabricating parts and stamping parts, right? How can we 3D print the innovative stuff instead of fabricating? So using those kind of techniques that we have today, but then pushing that towards fast flow. People are figuring that out. And so we have to challenge our hardware folks, where are we in that adoption curve? Certainly we don't want to end up like some of the software companies today that the Amazons and the Googles are eating our lunch, right? We want to be more innovative in that. We want to be more ahead of the curve. Hardware's already seeing the benefits. There's a great video out on Vimeo that from our summit, not this last year, but the year before, so it's about a year old. But one of our lead consultants that consults in the hardware space, he did a great presentation on feedback. And these are direct quotes from many of his customers where he consults with, right? It reduced risk early, it eliminates waves, it's making our designs more simple, it's driving simplicity, we're getting faster feedback, right? So hardware is already seeing the benefits, right? So we just need to start adopting these practices. And really what this tells us is that we want to be principle based. So all those all the parts of SAFe where hardware applies, those are really just an outline, if you will, for our talk in the course here, right? We want to enable business agility. We want to assume variability. We want to embrace variability and preserve options. We have to design our systems for change. We've got to organize around value. So these are really the lessons of the course that, again, we're piloting now and experimenting with. And these are, again, just a bunch of example slides that we're going to experiment with. So let's get into it. Let's talk about organizing around value for hardware development. We all know this, that value does not follow functional silos. Yet, especially in hardware engineering, less so in software, but certainly in hardware engineering, we have many silos, and those silos have handoffs, and they don't talk frequently. And if we look at flow across silos as a standard lean kind of diagram, there is a certain cycle time of the work that needs to be done. The delays and the waste are all in the wait times, right? by not having people aligned around value, there's a request and there's some kind of CCB board that has to meet. And certainly there's an hour to approve it, but it might take, 6 weeks for that CCB board to meet, to be able to address it. And then it moves to technical design, and, I'll get to it in a couple of weeks, and you'll be able to do the technical design, handoff. The idea is we want everything from the authority to decide what to build all the way to designing, building, testing, ideally fabricating. We can bring 3D printing in here, or we've got space in the manufacturing site to be able to do capacity, all the way out to authority to verify, right? We want to reduce that flow as quickly as possible. Now, certainly there are larger chasms in hardware. We do have to manufacture parts. We have to assemble them. We have to move into an operational. It's easy in software to push things into an operational environment. We figured that out, right? We can do things with virtual machines and software factories that quickly get changed out into an operational world. In hardware, it's typically we've got to take machines offline, equipment offline. There's an installation procedure and practice. There might be a verification once it's installed. It's got to be signed off on. So there's certainly a couple chasms we'll talk about, but that is the goal: to how fast can we flow value through this system. All right. Another challenge is we have to balance deep specializations. There is a lot of siloed work that goes on in hardware, right? So certainly agility requires that we have specializations, but it also implies that we have to collaborate. So we don't want to tell our hardware engineers that being a T-skill, being cross-functional, being cross-skilled is more important than your deep silo. But the deep skills necessary, we certainly need a certain amount of deep skills to get the systems built, but that's not for the everyday work, right? A majority of the work to be done in a lot of these functional areas is pretty general stuff, right? So there's more value to the business to be able to have you assist and support other functions, as well as being able to do your deep work. So the cross-functional teams and cross-functional engineers is a more value to the business. So what are different strategies for organizing these cross-functional teams? So it really depends. These are all reasonable approaches for organizing teams, right? One example might be that we have a lot of dependencies, and there's a lot of frequent and unpredictable handoffs between people. So we need our hardware and our firmware and our software, and maybe even some business folks all aligned trying to find out what we're doing. A lot of experimenting, a lot of ideation. So there's a lot of unknowns, uncertainty, unpredictability. So we need that close collaboration. Then typically, it can evolve too. That the hardware, we're developing the hardware. There's not as much ideation. I'm just going to be designing my circuits, generating the next revelable board, 6 weeks from now, maybe a couple months from now. So I don't need the software people and the hardware people to have daily stand-ups and be planning together. So the hardware is evolving to kind of more of a platform, and the software, we can manage the dependencies by having two teams. They can just coordinate them. And it's safe we've got those kind of coordinations across dependent teams. That's part of an Agile release train. Right? So these two teams might be on Agile release train. And then eventually, and I would mention in a different context, well, the hardware is a platform, and we have these. We're going to be producing revisions of our board or of our parts every some kind of milestones downstream. It might be six weeks or 2 months, and then 2 or 3 months after that, and then another couple months after that. So there is a well-known roadmap of when you're going to get the next rev with the new capabilities and new circuitry and new peripherals as part of the design. So the software, so there is a roadmap here for some kind of a hardware value stream. The software folks can build on that roadmap. They can do their planning of their roadmap on top of it. And that's the notion that we have a hardware value stream that's relatively separate from the software stream. And there's still, of course, coordination, because as we know, right, the roadmaps and our plans they're all subject to change. But the message here, though, as we start to organize around value, it really changes that traditional engineer's role. Historically, an engineer was a silo. They probably, I did layouts. That was my goal. And I supported maybe 2 or 3 or maybe even more programs. And I did layouts for them. And my functional area that managed all layouts, their job was to make sure that there was enough layout capacity to support all these different types of programs. We're moving that. Now, you are now a member of a cross-functional team, and you have your certain, your expertise, certainly. but you need to help the teammates, right? Success is just not individual success anymore. Success, that's the last bullet on the bottom. Success is really team success. So if there's work to be done by the team and it doesn't involve layouts, I may get involved with helping other people. And we have a great video from a director of engineering for a company, Whitronics, that develops the hardware that goes on trains. And he talks about the fact that he's got some of his mechanical engineers doing things with Arduino switches, and electrical engineers updating schematics, and for certain mechanical designs. And they just really he says curiosity. We want people to be curious about not just how their part of the system works, but how it works with other parts of the system, right? And grow those cross-functional skills. All right, next topic here is to embrace variability and preserve options. And this is where we really bring in that customer-centric focus, right? We want to apply design thinking, that notion of being customer-centric to the products that we build. And it's interesting, we walk through an exercise that hardware really has a lot of customers. Certainly the ultimate end user is a customer, but a lot of times our hardware is embedded in a system. And while certainly the end user is going to do some experience with that hardware component, maybe it's the electronic brake and the anti-lock brake controls in your car. Certainly, I expect when I slam on the brakes that those anti-locks take effect, and it doesn't cause my car to skid. It allows me to maintain control. However, there is a lot of other customers in terms of how we're going to manufacture that electronic control module, and what if it has to be replaced and deployed in an operational environment. What if the algorithms for anti-lock braking change? How do those algorithms get updated and upgraded and maybe delivered to either be replaced in a flash drive or over their update? Right. So there's a lot of other customers besides just the end user with hardware, because they have to be manufactured, assembled, installed, operated, upgraded, and having hardware engineers think about who all those customers are. That's who we're really designing for, right? Designing to make sure all those things are done, and that's nothing new, right? We design for manufacturability, all the other things. But it's really a customer-centric approach, an empathy-centric approach. The notion, though, is we really want to pull the learning forward, right? We want to create new knowledge that flows through the system faster. So there's a lot of experimentation that goes on in Agile, right? In hardware. We do trade studies, we do models, we do simulations, we might 3D print parts. So that's where we want to evolve this fixed to variable solution intent. This seems like it's a little off in terms of my slides. Yeah, all right. I think we might have switched modes here. This slide's really talking about the sense that we're going to make new knowledge that creates our fixed variable solution intent. SAFe has the notion of, as we design our specifications up front, there are certain things that we know, right? If you look at a traditional process that we follow a traditional process, we like to specify everything up front, right? We're going to get rid of uncertainty because we're going to specify everything, right? If we specify everything, that will make the rest of our development more predictable. And if we plan everything, we come up with some kind of master schedule, that would make it more predictable. Well, what we're doing is we're specifying and planning things that are not validated, right? So it's only later on down in the system that we find out that it didn't work. We have this massive disruptions, and we have a lot of rework to be done. So instead, let's let things vary. There's certain things that we know. Let's validate those things early, and then let other things vary. We don't have to make every decision up front. It's just our process that's forcing it. There are decisions that can be made later, made downstream. And how do we make decisions and validate them? Well, we do that by experimentation, right? These trade studies. So it's important to note that if we allow these flexible specifications to occur, right, over time, the work that we're doing down here, this red enabler work, that's going to be doing two things. That's going to be narrowing our focus towards an optimal solution. It's going to be maturing our product technology, and it's going to be recording, right? We're going to eventually get all of our shall statements, all our design decisions made. We're just not going to make them all up front. We're going to make them by the time that we're done building the product. So that's where we record this fixed variable solution intent, right? So that is SAFe, what we call our solution intent. It's fixed variable. Here's kind of a decomposition if we were to break it down. It manages all our requirements. It manages our system designs. It manages our domain models, right? If I'm an IBM customer, this is probably my doors model or my Doors Next Gen model. This might be a Rhapsody model. We want to connect those. This is a test model, manage it maybe Rational Quality Manager, and we want to connect these things for traceability. And then I might use OSLC, some of the other IBM technologies to integrate other tools, right? The domain-specific tools, electrical CAD tools, mechanical CAD, other tools, so that we can have a nice integrated model and ask, do analysis on that model and simulations and ask it questions, what-if type questions. What happens if I make a change? What will be the impact of that change? So that's the notion of safe fixed variable solution intent. It's a repository of decisions that have been made. It expresses what the system is today and what it will be tomorrow. And it also can be used as we move towards a model-based engineering approach, right? Towards doing our systems, right? We got system engineering models. Those can be connected to other models. We can run these simulations and we can learn in the virtual world. So that's one way we're shifting learning left, is by doing modeling and simulation. Excuse me, and we hear stories about, we can run all kind of regression analysis tests. So then really the changes that we push into production, we want to experience those changes because they help us validate the models, right? The models become the way the world behaves, and we use the production facilities really just to validate and update the models to make sure they mirror what's really going on in the real world. So how do we make this happen? How do we support this notion of fixed variable solution intent? How do we let things evolve? What we want to do is we want to move away from rigid shall statements that don't allow teams the flexibility to implement their solutions. So instead of picking a technology or giving them a fixed constraint, we want to give them variable specifications. That second bullet. And how many times have an engineer bumped into a spec that said 12? And I was thinking, well, if it was only 14, I would be done, because I can do 14 volts or 14 grams or 14, whatever looms for lightness, whatever the constraint is, I'd be done. But somebody put 12. And why did they put 12? Well, because it was way back early on in the program and it was time to pick a number, and I picked one, and 2 years later, somebody is subject to that number and they have no variability to be able to add more value. And, maybe it's the case if we bumped it up to 14, it would save a lot of money where this engineer is working, and the people that would have to compensate for that 14, it's not that big of an impact for them. But because we fix everything up front, we're subject to those constraints all the way through the building of these systems. So huge value in the notion of leaving things flexible and making decisions later. Really good book by Alan Ward on lean product development. It's an old book, well, not old, 20 years old or so, but he gives a lot of examples in the automotive industry how Toyota would give variable specifications to their suppliers. And then they would kind of compete and say, if we give you the extra 2 inches, or we give you the extra 2 volts of power, what value could you add to the vehicle? So they basically overprescribe the car, right, in terms of allocations, but they negotiate those allocations with all of their suppliers, internal and external. So it's a good way of thinking about variability and how that can add value, where a lot of times we think about variability as being evil, right? Evil and uncertain. It's really adds certainty and makes things more certain downstream because it's built on validated learning. There is this notion of we have backlogs, we have requirements in both the solution intent and backlogs, right? So we mentioned the solution intent. Certainly, we've got requirements, the shalls. We need fundamental requirement specifications because we have to test the system against those requirement specs, and that's part of compliance, right? We can't launch our avionics system or sell our automobile unless we comply and show that compliance. That said, we don't need detailed specifications, right? How many of us in the past have written detailed specifications of 1.1.2.1.3, the system shall, right? That level of detail, we can push that off to the teams in the backlogs, right? We need sufficient specification and solution intent to align the teams on what we're going to build and to serve as the source for compliance information. Beyond that, we decentralize those decisions and they get placed in the backlog. So the solution intent will drive what teams and Agile release trains put in their backlogs. And then certainly as we learn from doing, as we go build the system, we might make adjustments. Part of the definition of done of a story or feature might be go back to the solution intent and make sure the design is still correct, or make sure we haven't made any changes. We don't need to make any changes to the requirements, right? So this is a cyclical model. So solution intent drives those backlogs, but also the implementation from those backlogs to make adjustments back into the solution intent. All right, I want to talk about applying a common cadence here. Hardware domains experiment through the times they deliver. So they experiment. We talked about this before. They might be doing mock-ups with breadboards or experimenting with, you know, foam prototypes in a wind tunnel. And certainly they do modeling and simulation and equations. And they do this to mitigate risk. But historically, those prototypes aren't aligned. Here we're looking at maybe a camera, and there's a mechanical, there's mechanical enclosures being designed, and it's being modeled by, you know, whoever's that functional area in the mechanical doing it. And there's an FPGA development going to do digital signal processing. I have to take that image sensor and I've got to turn that into some digital signal, right? So I've got some, you know, logic that I'm designing for my FPGA, and there's a circuit board being designed that's going to hold the image sensor and the FPGA, and you know, a lot of times all these functions are working in silos, right? They're building their own, they're doing their own experimentation. I'm doing my modeling in the dev kit, and you know, the PCB is going to be Rev 1 of the printed circuit board, and Rev 2 and whatnot. Well, really what we're trying to do is align those functional areas. So maybe put those folks on the same team and say, hey team, in the next increment, a month from now, 6 weeks from now, what could you show me that's integrated? Could you show me video signal processing? Could you somehow validate that the power is not going to interfere with the video? You know, what could we learn as an integrated solution on a more incremental cadence, on a more incremental basis, right? So that's trying to integrate the system on a more continual basis. And how fast what's the time between these integration points? What is the time? Oops, excuse me. I thought I had my pen here, but I undid the pen. What is the time the delay here, right? This is our learning cycle. How fast can we learn, right? And that's a fundamental thing in the lean startup, is those organizations that learn faster are going to be the ones that succeed, right? How quickly can I gain knowledge? Otherwise, I'm not going to gain this integrated learning until some schedule calls me to say, take your stuff, and your stuff, and let's integrate that and put it together. That's on the schedule somewhere downstream. Well, no, it's not on the schedule downstream, because we need to integrate these things more quickly to go learn, make adjustments, and continue on. If you look at, for example, in SAFe, we talk about these increments being, we talk about, we say 6 to 12 weeks. The big picture shows 5, I think, if you look at the big picture. So people usually do it quarterly. If you look at automotive is on a 6-week cadence. They're integrating their vehicle platforms across internal and external suppliers every 6 weeks. That's not to say we're going to do a new engine block every 6 weeks, for example, or a new piston rod, certainly. But certainly things that are involved with firmware and infotainment, and there's a roadmap that says every 6 weeks I hope to be able to show X across the whole vehicle platform. And the folks that are contributing to that innovation, whatever's going on those 6 weeks, they contribute their solutions, hardware and software, right? And that's really the vision, is trying to shrink those integration cycles down so that we can learn faster. So that's the goal, is to apply a common cadence across the entire organization. You go to automotive, all 12,000 of their engineers at a big 3, they're all in that same 6-week cadence. And they force all their suppliers on that cadence, right? Common cadence is how we integrate the system and be able to look at what it is. So we want to have a roadmap to say, here's what we hope to be able to demonstrate and show or learn every increment downstream, right? How do we build the system incrementally, learn and make adjustments? How do we move from the next version, right? This is software is easy to do incrementally, right? Because it's pretty easy to press a button, go do a build, and then get the next increment. Hardware may require manufacturing things, right? So really we have to make that investment. Software's made the investment over the last couple of decades to lower the cost of integration, building and integrating, right? So if we look at this U-curve optimization looks like this. Here's the cost of delayed feedback. If we integrate every day, we have very little cost of delayed feedback, so we're getting feedback every day. If we integrate every year, well, there's a cost to not learning within that year, right? There's a holding cost of not integrating to get that knowledge. That said, if we integrate every year, it's relatively cheap. We'll have to build and integrate the system once a year, versus I build every day, it's going to be prohibitively expensive to remanufacture, and it's not even feasible. So if we sum up these two cost of delays, here's that sum curve. And there's a U-curve optimization. It says the optimal economic integration time is every, 9 weeks, whatever it is, 12 weeks, 3 months, 6 months might be. Well, our goal is to shrink this curve down, take this curve and lower it lower the cost of manufacturing and integrating. And we do things, right? We do things like 3D printing. We'll talk about them in a little bit. If we can lower this curve, then that says, hey, the optimal integration time is not every 6 months or 9 months. It's every 3 weeks. It's every 9 weeks, right? We're investing in lowering that cost. And that's really what software has done the last couple of decades, investing in automation and virtual machine. Luckily, VM had come out a couple of decades ago, so that whole notion of virtuality really accelerated the ideas as we build things in the virtual world, so we can start them up and tear them down quickly, and everything is code. We've got a lot of great practices built on the fact that we're going to lower that time and cost to do builds and integration in software. We want that same value in hardware. So what we're going to do is we're going to continually integrate, right? So if we lower that cost of integration, we can integrate now more frequently, and that builds us an integration platform, right? That's the integration platform. Initially, this is going to be a Frankenstein-y kind of thing. I'm going to use this legacy system over here and a breadboard to connect that image sensor, and I don't have a housing yet. It's just a bunch of wires sticking out in the lab, and that's fine, right? And slowly but surely, as we continue to integrate, it's going to move closer and closer to the real production-looking environment, right? Initially, it's lab, dev kits, and things wired together. But what that provides us is an integration platform for everybody else to build on top of and validate that we're able to make progress within the system, right? So we need hardware to come along to help us so hardware teams don't just deliver their final end product, they also deliver incrementally, right? And because we've lowered the economics, we're doing things like 3D printing, and we're doing things like other additive manufacturing, lowering the tolerance for manufactured parts. That's another tricky thing, is a lot of times we assume before manufacturing a part that it's going to go sit inside of a bunker for 3 decades. So it has to be fully qualified, and a lot of compliance work done to it. Well, these aren't going to go sit in a bunker for 30 years. They're going to go sit inside a lab until we make the next version. So, if we get 50 boards and 3 of them fry the first time, well, that's probably okay. I'd rather get the faster feedback than wait 9 months to get a board. I'd rather have a board in 3 weeks that are less quality than 9 months that are fully qualified. So a lot of times we have to go internally in the organization and start to, as we lower these costs. A lot of these costs, this time and cost, isn't just manufacturing. It's also internal compliance issues as well. So as we reduce those costs, we can better integrate the solution and have an integration platform to build on top of. All right. Business agility requires fast feedback through frequent learning. So as we mentioned before, we've got all these hardware folks. There are many customers to hardware, right? It's not just the end customer here. There's also the customers we had mentioned before. There's other engineers. There's people that might consume our data that we're producing, right? The data folks. There's also manufacturing assembly. There's those operators out there, right? So we need to learn from every one of those. So we need to reduce these learning cycles. How fast can we get feedback, right? And have the capacity to be able to respond to that feedback. We want to build that in. There's multiple feedback loops in hardware, right? Certainly where we're ideating and modeling and simulation, as we move to manufacturing, and then as we move into the operational environment, right? We get feedback, and ultimately we get feedback from the real customer that's out here. So we want to create modular designs, right? So this is really the next step. I apologize. I think I'm missing some separators in here. I don't know what happened to the slide deck, but I apologize. So we're moving into, I'm going to take a step back here real quick. I think that was in slide, say, 9. We're on slide 31 now. Yeah, we've moved into designing for change. I apologize. My slide separators aren't there. I added one for build incrementally. We talked about him. I'm sorry, we looked at variability preserve options. We really kind of moved into design for change now. So what slide was I on? 31, I believe. Yeah, so we should have a nice separator in here, designing for change. We need to design to support efficient change. And this is nothing new. It's well known, right? We want to have modular components that communicate through well-defined interface contracts. But the interfaces aren't just software APIs, right? We have interfaces that are electrical interfaces that can be standard like HDMI, but there's also physical interfaces as well. How is the camera going to mount itself on the body or the rearview mirror, wherever it's being mounted to? What kind of forces apply and what kind of material has to transfer. It's not true in the camera, but we might have to be transferring electricity, or we might have to be transferring weight or heat or radiation. There's some. We have to make sure that the join here, whenever we join these things, we can transfer those kinds of properties. What interfaces do is they allow us to have frequent independent design iterations. So if I'm the camera team, as long as I've got this nice contract, I can give a new revision to every one of to the people that use me. First off, I give a dev kit, and the dev kit's sending out my HDMI signal. And eventually I give Rev 1 of hardware and Rev 2 of hardware. And it's got the FPGA in it, it's got the digital signal processing, and it's getting better and better. It's got the new optical sensor as we move forward. It's getting a higher quality signal, and we've got a better light detection with the new optical sensor. But vehicle control doesn't care. They just know they're getting a signal and then continually test against that. So we're writing a way to integrate the system more frequently because we're giving incremental solutions along the way. Likewise in mechanical, right? We could initially start with the enclosure for the camera, and we might want to integrate those models. We talked about model integration in the last, earlier we talked about solution intent, and we can validate that maybe the components will line up, and there's maybe some screws. We're going to connect these with screws so the screw holes line up. Whatever. We can validate them through models. We can validate 3D printing, so we can get earlier feedback before we actually go manufacture the product. So integrating these models, being able to generate parts earlier with 3D printing. And then ideally, a lot of places, like I mentioned, SpaceX isn't going to manufacture parts. They're just 3D printing everything, right? And as 3D printing evolves and becomes more powerful and more cost effective, I certainly won't work at scale, right? We're not going to manufacture, cell phones with 3D printing, although maybe we will. But for us in the areas where we don't have the extreme volumes, 3D printing is becoming a more viable option. And what it does is it makes that CD pipeline a little more viable for hardware too, because I don't have to go off and manufacture a part and assemble it. I think in the the SpaceX rocket, they talked about the hundreds of parts they have eliminated by 3D printing, right? They don't have to stamp a bunch of parts and then assemble them later and all that delay. They just 3D print the rocket. It's got 3 or 4 3D printed parts, and they put them together that way. Really interesting way when we think about it, right? 3D printing. How do we design for changeover electrical components? Certainly, if we want to favor. There's kind of 2 sentiments here. Is where do we put the logic, right? So I've got logic inside of the camera. If the camera is deployed out in the field and I change that logic, I've got better logic to be able to better detect street signs in low light for the reflectivities change or something. If that's even a word. So how would I change that logic in the camera? Well, if it's placed into an ASIC part, ASICs have that logic burned into them, right? They're manufactured with the logic into them. Cannot be changed. We'd have to go physically pull out the ASIC and put it in. So we're seeing actually a trend more towards more FPGAs, more system on chips. Excuse me, because they're reprogrammable, right? We can update them in the lab. They're more easily to be reprogrammed, or even in the production environment, they're more easily reprogrammed. Also, if we do want to replace the camera, how is it mounted, right? Is the camera soldered to the vehicle? Is there a solder connection connecting the camera to vehicle control? Or is there some kind of connector, right? Can we pull the camera out and unconnect it and place a new one in? We have to design these things in. Same thing with mechanical parts, right? When mechanical parts are joined, is that joint a weld? Is it through some kind of a non-permanent joint, like a screw or some kind of other linkage? A bolt, a screw versus a weld. So we've got to design these things so they can be more replaceable and kind of predict in our mechanical designs which can be replaced or not. Now there is trade-offs. Certainly, if you go back to electrical, ASICs are much higher performance, especially when compared to how much power and unit cost they produce. They're cheaper to produce in unit cost, and they have a lot less and use a lot less power. But again, they don't offer that programmability. And I've talked to Bill Chone over at Mentor Graphics, and they have a lot of design tools, and they do they get data from their design tools. He was saying that in the electrical CAD world, there is, I think it was an order of magnitude less unique ASIC designs. Now certainly they still produce a lot of chips in ASIC because my cell phone here, there's probably a lot of ASIC designs because they're going to do high volume manufacturing. So in high volume, certainly ASICs have their value. But for kind of some of the lower volume things, it's more cost effective, total cost of ownership, right, to make those programmable, right? So we're actually seeing a lot less unique ASIC designs going on. Mechanical, right, modularity is going to add size, weight, material costs, additional manufacturing costs. It's very easy to manufacture and weld something. If it's got to be assembled with bolts and whatnot, then it gets more costly to assemble. But it really comes down to business agility, which we're trying to connect this whole thing to, right? So we started out with a business agility conversation. What does the business demand? And let's not sub-optimize for unit cost when we want to understand our total cost of ownership if the system will evolve over its entire life, which in a lot of these systems is years and even decades. All right, the last section here I want to talk about is built-in quality for hardware. The notion here is that if something's useful, we should do it all the time, right? That's an extreme programming motto. That if back into the extreme games back 20 years ago, when XP was invented, extreme programming was invented. It was they were kind of a takeoff on the Olympics, right? If Olympics likes downhill skiing cool. Well, the X Games is going to ski off cliffs. If downhill skiing is cool, extreme downhill skiing is probably just skiing off cliffs. And they have that same motto that if testing is a good idea, we should be testing all the time, right? We should automate tests, and on every developer change, we're going to rerun a bunch of regression tests against it. If code reviews, if reviews are a good thing, we should pair up. We should only do coding and design in pairs because we want to review all the time. So that's a mind shift to shifting things left. Testing and reviews are all shifted left. They're as far left as we're doing them simultaneously. As we do designs, we're reviewing them. As we make changes, we're testing them. So it's almost simultaneous. That's our goal. And really what it is, it's back to the Agile testing pyramid. And the Agile test pyramid says this, that component level are fast to run, they're cheap to run, they're relatively inexpensive. So we should have those. We should catch most of our errors down here. Because these system tests, they require much larger platforms and costly equipment, and they're costly to set up. So they're very, very expensive and they're very slow to run. However, most organizations, because they haven't invested in tests down here, do most of their investment of testing at the top. Most organizations have inverted pyramids, right? They don't spend a lot of time having developers or engineers do tests, certainly in the hardware space. So they have to reveal most of their errors at integration and system level tests, right? And that's not cost effective. Right? And that's really the goal of test-driven development and Agile testing, is to try to build up a nice bank of unit tests so that we can catch our errors down here and reduce the amount of testing time that has to be done up here. How can we build test-driven development in for hardware? So we've got some ideas, and these aren't standard practices, but they're ways we can apply this, right? The goal is that we want hardware's a little bit behind software, reminding ourselves that, but these are ways we can approach this. The idea is we want to have a nice red-green dashboard. On any change I make to an electrical design or a mechanical design, I want a series of tests to rerun and tell me if I've broken anything in that change. What might that look like for electrical engineering and mechanical engineering? Well, we could start electrical. It's pretty straightforward because most electrical models are VHDL or Verilog. They're very software-like. We can build code while we're building our VHDL or Verilog code. We can build in unit code testing for them. There's also, in fact, we talk about this. There's sites, web blogs that people are posting in mechanical, where they, in their mechanical designs, they have design constraints that they're designing around. So basically, they write some equations and write formulas that take the design constraints, and coupled with the calculations that they're doing in their mechanical design, they build a nice little dashboard of red green and say, here, your designs are outside your tolerances or outside of the constraints you've specified over here. So they can go into the mechanical designs. What's really cool about that is we know this in software is that when we do any design, we're going to come back into this design sometime later. It might be tomorrow, it might be 6 months from now. It's really hard 6 months from now to come in and recall where we were and to go make a change reliably. So that backstop of having built-in quality of those test cases is really powerful to allow us to come back in an electrical model or a mechanical model and go make a change, ensuring that those regression tests are being run automatically for us behind the scene. And ideally, we'll go back to the Mentor graphics and those folks and say, you should be building these into your CAD design tools, right? They should be part of the standard flow of the CAD design tools. And what that really is going to push us towards is building a continuous delivery pipeline for hardware, right? We are going to be building these systems for a long time. Our focus is historically, though, build the system once, build it the right way, and we'll say high five each other. Thank goodness we got through that. Let's move on to the next system. But in reality, that system is going to evolve, right? We didn't just produce it one time. It's going to have upgrades. It's going to have new capabilities, new features. We're going to be contributing to this system for years or even decades in a lot of systems. Like I just got off the phone with a government agency that, we had these systems that we had planned to put in production for 25 years, and now the new lifespan for them is 50. Help us, right? We need to move to Agile. So a lot of these systems are in place for decades. So we want to build not just the solution, we want to also build the solutions continuous delivery pipeline along with it. And if we have a continuous delivery pipeline that makes changes more predictable and more reliable and simpler and faster to flow through the system, that really changes our mindset, right? We can actually deploy this system early. I don't have to get all the capabilities in the system. I just have to get enough to make it useful so that I can start getting feedback. We're going to build the system early, deploy it and evolve it, as opposed to build the whole thing and get it released and then support it. Totally different mindset change for us. And software's moved to that mindset, but the cyber physical system builders, not quite there yet. We need to get them there. It's certainly the case that we will have different CDPs for different types for different components of the system. Certainly software follows this, development, system level test staging, production environment, where hardware follows one that goes more through design, verification, manufacturing, validation, and operation. A little bit different flow, right? So, and even within hardware, different hardware types of components will probably follow some kind of different continuous delivery pipeline. But the sentiment's the same, right? We want to take a small change, get it out of the developer's environment as quickly as possible into richer and richer context. That's all we do here. Take a small developer change and move it into richer and richer context as quickly as we can. And some of the unicorns talk about taking that developer change, moving through the system. We do thousands of releases a day kind of thing. Doesn't mean it moves through in a day, but it can move through within a week. Spotify talks about, we like every one of our developers to put something in production within the first week of when they arrive at our company. So they get that mindset of continuous flow, continuous delivery. Okay. So we can early on start testing inside of models, right? Models provide good economical testing. So in the design verification in that first cycle, right? This is where we're doing a lot of modeling. So we should be able to build fast feedback loops, fast built-in quality inside those models. We talked about a couple examples in terms of TDD for electrical design and TDD for mechanical design. People are starting to look at how can we build that quality in to apply test-driven development. What that does, if we can integrate in that virtual world, if we maintain these models over time, a lot of times when we get done with, I should back up here, when we get done with our camera model, the model in the loop, as we move towards software in the loop and eventually have the hardware in the loop, we throw away those models, right? We don't need to maintain those, we need to support them. But if we do maintain and support them, then they become that digital twin for the physical world, so that we can do a lot of experimentation and learning back in the model world. And then the physical world just validates that our models are accurate. And as Joe Justice, Wikispeed, if you don't know that organization, I encourage you to look them up. They're doing a lot of great things with Agile hardware. He says, I don't know if it's true or not, but he claims that our crash simulations in our models are so accurate that the U.S. government now accepts them. In other words, if we change our vehicle, we can run a regression of a crash test in a model instead of crashing one of our vehicles, and it still complies with regulations. Kind of cool. And that's the goal of the virtual world. We talked about those automated pipelines and software. We made the statement that the goal is to take a small change here and move it through as quickly as possible through these increasing richer contexts. And along the way, we're performing a series of tests along the way. And these are standard software tests, static analysis, quality tests, environment tests, et cetera. We've got the same kind of pipeline in hardware. It just looks a little different, right? We do design, verification, manufacture, assembly, operation, installation. And we do quality checks. If you're in electrical, we do a bunch of quality checks along the way here, and mechanical as well. Can we think about how to automate those tests so that they're automatically run on small changes? I think we can think about that, especially in the modeling world. We have a couple of chasms on our hardware CDP though, and those are important ones, right? When we move to the physical world, when we actually have to build a part, right? That's one chasm. There's another chasm too as we move to installation and operation, right? We have to take things out of operation, the operational environment, and update them. Let's talk about each one of those chasms individually. As we move from the virtual world to the manufacturing world, well, we talked about how we can U-curve optimization. This before was for integration. This time it's for manufacturing costs. can we lower the manufacturing costs of the parts that we're building? You know, additive manufacturing, I talked about 3D printing, right? I don't have to wait for a manufacturer to make my part and get it back to me. I can make my part locally, right? Maybe tomorrow even, maybe overnight, I'll come in and it's done, right? We talked about do a build every night. We can do a part every night. You know, software does the nightly build, and manufacturing might do the nightly 3D printing. Also PCB, there's the notion of PCB boards today. We're starting to actually be able to do 3D printing, added manufacturing for printed circuit boards. And we already talked about lowering the quality standards, right? These things aren't going to be sitting out in bunkers for 3 decades. We want to use it to validate our integration, right? So those are the things people are already doing to move across that part of the chasm of the CDP for hardware. And the third one, we alluded to it a little bit. It's really just how we design, right? We talked about, can we design and make things more easily to change in the operational environment? Tesla today does over-the-air updates into their cars, right? It's relatively, they probably don't have a lot of ASIC parts in there, right? They have a lot more FPGA system on chips because they're able to update over the air and be able to put new capabilities, new functionality into vehicles that are in operation. The last one though is in modular design, right? It really comes down to how we design the components, which we already talked about. As an example, Tesla knew when they sold the Model S, when they first sold the Model S, it was not going to have the brain, right? The brain engine. They were going to make their own, right? They're using Mobileye or somebody else's CPU. They knew they were writing their own, but they went and sold the car anyway. And they had an upgrade plan that you bring your car in, we'll swap a board out, and we'll be able to upgrade those vehicles. So understanding where within the system we're going to need to be able to upgrade them. Do we want to place the cameras? Do we want to play the hardware? Making that upgradable so that these cars have longevity, so that our, we can meet our 10, 20, 30-year milestones. And it allows for things like instead of manufacturing, we can 3D print in the field. So I don't have to manufacture a part and get it to a dealer. I just say, hey, here's the new spec, dealer. You print your own parts. You can just print your own parts and assemble them right there at the dealership. All right. So I thought I had put a closing slide on there, but anyway, I'll jump back to the front slide. Thank you all for attending. These are ideas that we're ideating on, getting feedback from the community. We would love your feedback as well. It says up there, my name's Harry Kahneman. You can reach me at harry@scaleagile.com. If you've got insights or examples or questions, feel free to reach out to me. I'm happy to take them, and we can take some questions now if you'd like to.
Thanks, Harry. Thanks, everyone. If you have any question, you can unmute yourself and just ask the questions before I start my questions.
Nobody has questions?
Oh my God. So that's a chance for me to ask a question. You mentioned about building quality. So you mentioned about test-driven development. You mentioned about some of the concepts here. What about the other aspects that we know in software? Something like technical debt, something like refactoring. How those apply, if they apply in hardware?
That's a great question. So the technical debt. I am not a hardware engineer, right? So certainly as we design electrical designs, right, with VHDL, I have done a little bit of FPGA programming in my day back in college. Certainly they're software-like. They can be designed and refactored. But even in mechanical designs, right? Mechanical designs they have units that they have units in modular designs that they grow into their mechanical designs as well. Understanding how those designs can be redesigned and reused. So like we refactor. We'll look at a part of the system. We'll look and say, hey, it'd be better if this part was more modular. We can apply those same modularity principles to hardware as well. But I think a lot of it really, I struggle with telling hardware engineers how they should do their modularity. I think that's something that, frankly, we're going to have to ask the hardware engineers themselves. Here's the principle. The principle is make modular designs, be able to reuse your modules. I think to some degree they're doing that now, certainly in electrical design and probably mechanical design as well. But I think that's something we go to them with the principle and we ask them to say, hey, is there value in refactoring? historically there's been no value refactoring because they were one-offs, right? My job is to get this part designed, and I'm moving on to the next solution and the solution after that. Now maybe there is. Maybe there's a library of components, right? We have software libraries of components that we strive to reuse because we've, over time, as we've thought more about reuse, we've identified, reusable components. That might be the case in hardware, but I think we're a little early to be able to, the spirit of making things modular, be able to refactor things, maybe make components more reusable, is certainly a goal. But I think that we're a little early in being able to tell them how to do that because I don't think those practices have been thought out and proven in the hardware world yet. Good question, though. Really good question.
Because what you mentioned about Tesla Model 3 seems like refactoring, kind of. If we put it in that context, I don't know if it looks like this or not.
The example, what was the example where they replaced the brain, the hardware board?
Yes.
Well, I think it was, I don't know that they refactored the board. They just knew that the hardware in there was not going to be sufficient for full autonomy, and they knew that. But it was sufficient for the current needs, which they were advertising and promoting, which was, I can stay in my lane, I can adjust the speed of the car in front of me, I can respond to an accident, but I can't detect stop signs and street lights, and I can't do all that recognition. Differentiate between a bicycle and a fire hydrant, those types of things. I need much stronger compute power to make that happen. So they were able to design a system with cameras where the cameras don't need to be replaced, and there's enough bandwidth in the bus of the vehicle, right? The communication, right? The bandwidth to get the images to the board. There's a lot of articles I've looked at them beyond my comprehension about people have taken the two boards and analyzed them and looked at the signals that get sent to them. There's a lot of articles you can go read, but basically they just knew they were going to have to replace that brain. So that was a design point, right? That was an integration design point where they knew they were going to do an upgrade, and they still can, right? Since those other Teslas, if there's a next gen version, as long as they don't have to replace the cameras, they can upgrade that board. They can upgrade that board again. So I think it's less of a refactoring and more of a design. And I would call that design for the continuous delivery pipeline. That was an area where they recognized we're going to be able to swap this out. It's kind of cool as you point that out with the Tesla Model 3. If you've ever seen a Model 3, the dashboard, it's nothing. There's no dashboards or instrumentation. It's a monitor. They basically have taken a computer monitor. So it's almost as if, if something goes wrong in any of the computation stuff, they'll just ship you a new monitor. And it could just be 3 bolts and it's a user replaceable part with a connector, and you put it back on and you're done. Because Tesla doesn't have dealers, right? They don't really have the capacity to maintain errors in vehicles. So they need operator maintenance, right? The end user maintenance. So they've lowered the cost of the car by getting rid of that dealer maintenance stuff. Talk about needing to build quality in. They're an example of that because they do not have, the notion of dealers and maintenance areas. You can't go take your car back to a dealer because there aren't any dealers. Interesting. Other questions?
Any other questions?
Well, I'll thank you all for the time. If you have further questions, for anybody watches on the video, please reach out to me, harry@scaleagile.com. We love feedback, so please give us some.
Thanks a lot, Harry. Thanks for everyone attending here, and happy holidays.
Hey, yeah, thank you. Happy holidays, everybody.
Thank you.
Okay, thanks, Mark. Thanks, Harry.
Thank you. Thanks,
Hey,
Mark.
my pleasure. Thanks for the invite.
Bye-bye.
Appreciate it, guys.
Bye.
Bye.